Yeah, hiya. I'm David. I'm from Machine Learning Group here at ARM. I'm going to talk about object detection at the edge and why this is hard. And I'm going to ask some questions about why this hasn't been addressed more. Did something just happen? Or is it still in the mic? Yeah. Why do we care about object detection at HD in particular? So cameras at the edge, in your mobile phone, in your home camera, in your car potentially, have HD plus resolution sensors today. So maybe HD, maybe even 4K, depending. The high-res sensors are there. What you will read in academic literature about object detection is that everything is running on 300 to 600 pixels. And what does this mean? In an object detection system, if you can detect an object or not is going to be closely tied with how large it is in pixel sense. So if you have something that's 50 pixels big, you have a reasonable chance to detect it. If something is 10 pixels big, it's game over. So anytime you resize your input down, you're throwing away stuff that you cannot see anymore. So, as the slide says, it kind of roughly depends on your optical system, your sensor, your lens, all this other factors. But if you downscale your image by half, you're going to throw away small detections. For this reason, it's desirable to do at native resolution if you can. You have the sensor, you want to use it. So here's a lot of people having a run around. And you can see the people having a run around, and they're covered in detections. So the blue is in particular a class for head, shoulders. Okay? So you can easily imagine, I hope, that if I downsize this image by a half, you're going to lose a lot of this. A lot of this. And it's obviously not desirable. So we have the idea that we would like to do object detection at HD at the edge in your smart camera or whatever. Is it possible? So I won't mention any ARM product which is available. You can buy an NVIDIA Jetson if you like. You can buy a Google Edge TPU soon, but not quite yet. And what you're going to get is about 1 to 5, maybe teraops. Okay? And depending what you buy, you'll get a different number format. But you're going to get 1 to 5 teraops at the moment. Obviously, this is probably going to improve, but that's what you have now. And these teraops are not cheap. So if you buy this NVIDIA Jetson module, you're going to pay £400 for it. I'm not saying you shouldn't. I'm sure it's a beautiful product. You're going to pay £400 for it. So you better make good use of this £400. So consider a state-of-the-art object detection system. You may have heard of YOLO v3. It's very popular. If you naively scale YOLO v3 to a full HD frame, you're going to pay 0.4 teraops per frame, roughly. Remember, you have order 1 teraops to spend. So what are you going to do? You're going to get 2 FPS, which is not that good. A human walking around is probably walking at 1 meter per second. So your object detection system is in 0.5 meter gaps between detecting people. So it means if you've seen a person, and let's say you identified that person, you have them in some kind of database, and you've used some other deep learning thing to spot them, you've seen their face perhaps, you've recognized them and said, there's David. And then David's teleported. And then he's teleported again. So you're going to lose this track. It's not good. You don't want to be running face recognition on somebody every time you do a frame. So you can't do, well, potentially you can do YOLO if you're going to accept this, but something that might be more attractive is to do something a bit cheaper. So you can do tiny YOLO. So tiny YOLO is much more cheap. The detection performance is correspondingly worse, but you can do it. And you can run this at 30 FPS at 2.4 teraops, which you might be able to afford depending on your system. So you might think, OK, cool, we're done. I have to use a small model, but that's what's available in terms of compute at the edge. So maybe that's what I'm going to do. is that smart. I don't know why these images are kind of looking quite bad. They're not bad on my laptop. They're not even bad on this laptop.
Look at the arm.
Yeah. I don't know if anybody back there can do anything about it. But here's some friendly ARM colleagues walking around a car park at somebody's request. And, yeah, I mean, everybody has to do their bit. What you'll see is up here is a bunch of sky. It's terribly unlikely that you'll ever see a person there. Right? In this region of the frame, there's nobody there at the moment. There might be somebody there later, but there isn't now. So here's the question. Why do I want to spend a lot of computational power doing huge amounts of convolutions of the sky? Probably I don't. That would be excessive. Region proposals are not a new thing. They're certainly not invented by me. So I mentioned YOLO earlier. A competitor to YOLO is called RCNN. The idea is very simple. You slide a network across the whole frame, get a feature map, and using this feature map, you make proposals. You go, is there possibly something there? And if there is possibly something there, I'll have a better check. So especially for HD frames and larger, this is seeming good to me. Problem is, in faster RCNN, the network to generate the feature map is VGG16, which is itself 0.4 teraops per HD frame. So what are you going to do about that? So all these networks are trained and evaluated on public data sets. So there's public benchmarks, academic benchmarks. I have no complaints about the existence or format of these benchmarks, but it's important to know what they are doing. COCO stands for Common Objects in Context, I think. And inside it is giraffes. I don't commonly see giraffes as I travel around the UK. So I slightly take issue with the name, perhaps, Common Objects in Context. I don't care about detecting giraffes, and I certainly don't want to have a very big network that's very big for the purpose of detecting giraffes. Moreover, even if there are things I do care about inside here, like people, maybe I don't care about people in every different possible scenario that there could be. I'm unlikely to see a person standing on their head. If they are, maybe I'll miss them, but we have to make some compromises somewhere. And really important in here, no temporal information. So these are all one-shot frames. People are trying to win at this benchmark, so they're processing one-shot frames. They have zero temporal information to access. So a different idea, well, not too different, is to instead put a very small network over the image. So here's an idea. It's nothing but an idea. I don't want anybody to say that I think this is great. I think it's a reasonable thing to go for a try. And this guy is 0.04 teraops per HD frame, which is 1.2 teraops at 30 FPS, which is more than I'd like, but at least it's kind of reasonable. And we run this across the whole frame. This bottom layer of convolutions applies a simple classifier. And if something is seen there, then we'll send it to something more complicated to have a check. Moreover, this guy is running at 30 FPS, could be. If I miss a guy in a frame, I don't really care either, because I'm going to pick him up the next frame, or the one after. Right? So, here's my guy at 1.2 teraops per frame. Just as an aside, I don't want it to be the main focus of the talk, but I just mentioned that we're having a little play with how to implement this. So a couple of simple ideas is hardwire this CNN. So it means the weights are unprogrammable. You make these weights, thank you, hardwired. You're going to apply this network to the whole frame, every frame anyway. rarely want to change it or never want to change it, hardwire it. Second option, implement the CNN in logarithmic domain. So in logarithmic domain, your multipliers became adds, and your adds became hard, but you can do some fiddling with it, which is subject to patent, so there's no, no slide for it. But there is also an idea that what we do, so ROC curve for anyone that doesn't know, true positive number, false positive number, so up and left is good. So you want the most true positives you can get with the least false positives you get. So the perfect ROC curve is a vertical line straight up here. So blue is everything in floating point on a video I'm about to show you, and with some fiddling with the arithmetic, you can get most of this performance with something a lot cheaper. But it's kind of an aside for the talk. I'm going to show you what something like this looks like, and this is terrible because of the projector. So I can only apologize. But what you'll see is people walking around, and sometimes they're detected, occasionally they're not. Sometimes something that's not a person is detected. But I don't care too much, because I can throw that away. I can track people through the frame, and if they're there on consecutive frames, I go, I'm pretty confident this is a person. And if they're absent on consecutive frames, I can say something like, well, if it's an isolated detection temporally, then probably I don't care about that. Oh my God. This is how I know it's definitely the projector that's messed up, because this is black and white GIF. So it became cool for a while to, draw features coming out of CNNs. So here's a feature. So you can see what the CNN cares about, kind of. I mean, this is hideously upscaled. But I think if you're familiar with CNN literature, what you might see is that deep CNNs know bits of people. They might know there's a head. So this is a very shallow CNN. It doesn't seem to know anything really about people at all. It seems to know something about edges, perhaps. It's just for interest. I don't really care that it doesn't know about heads. It does an adequate job at this point. Oops. No, I'm not going to try and make the video rerun. Some closing thoughts is that actually people think that CNNs are doing great work, and they kind of are, but I think there's an insufficient quantity of people worrying about how tractable they are at the edge. At the edge, as I said, you have your 1 teraop, or 5 teraops maybe, something in that ballpark, and people are proposing deep neural networks which have a model size of like hundreds of megabytes, even not considering the ops cost. So existing benchmarks are kind of emphasizing this detection performance at all costs without temporal information. And I think at least it would be good if people could start, normalizing by compute cost. People put things in papers like, my neural network runs at 100 FPS on an NVIDIA Titan X. Like, whatever does this mean? Like, who wrote the software? Is it well written? What's the GPU utilization? None of these things are ever recorded. I think practical benchmarks should be taking into account HD images, which they're not. And at some point, somebody's going to realize, somebody more important than me, that object detection in still images and object detection in video is not the same problem. It's a related problem, but it's not the same problem, and that temporal information is there and to be used. I think perhaps the reason it's not been picked up right now is kind of a paucity of availability of labeled training data for videos. There is some labeled training data for still images, but not videos. And yeah, all the arithmetic I put in these slides was for a 1080p frame. 4K is already out there. 8K is coming. So yeah, there's a question in my mind of whether compute can keep up. I think that's me done. So thank you very much.
Is there any question in the audience?
So I understood that ARM is doing some Trillium IP blocks for object detection.
Mhm.
How does that perform better than current solutions on the market, or how much ops are we talking about?
Do you want a sales pitch? People who care about HD resolution input are rare. So if you go to Embedded Vision Summit, you will see plenty of people with an object detection thing, and I don't want to comment on the details of what they're doing, but I think I will say that their view distance is generally less, and we kind of guess that it's because they don't care about input at native resolution. For clarification, all results on this slide are not from the object detection processor. So,
Hi, I'm Valentin Radu from the University of Edinburgh. We had a very similar situation with face recognition and not being detected training on COCO dataset. But that's not actually part of the question. I was more interested in the customizing your model for a particular device. Did you run it on Jetson itself, or and how did you come up with the architecture for the neural network? Was it to optimize computation cost on that device? Thank you.
The architecture for this, if you squint, is stripped down VGG. So there's no particular reason to choose that. It's just that you choose this actually based on your compute availability rather than a particular architecture. I really wish people would stop saying they architected neural networks, because in my opinion, people just kind of burp stuff onto a page. And there's new ideas in there, like depth-wise convolution is a new idea, but if you're just like putting an extra layer or something, you're not architecting anything, you're guessing. So this is kind of a ballpark. This is roughly the right size thing. It's VGG, so I hope no one jumps down my throat like saying that's a terribly stupid thing to do, but that's the limit of how much that is designed.
So one question from myself. When you talk about temporal information, is your idea to use that as a recurrency in the network, or is it always offline, like in this case?
For now, temporal information is used as is done as a post-process. So you get detections from different frames, and you know your detections across frames, and you apply something after this. I think it's definitely something that should be put into the network, or at least try to be put into the network at some point. It isn't, and I think, again, this is because of paucity of training data of labeled video.
And do you think that may help reducing cost? Well
Yeah.
done, or?
Absolutely.
Is there any scope for using the motion compression that will go into the finished video on some of these things to help having to update the actual network?
Yeah, actually, somebody did this in ARM already, but it didn't. It hasn't made it into a product or anything yet. But yeah, I think it's not my work. I think if I recall correctly, they did have some conclusion that if you use something like motion vector out of an ISP, that you can do every small number of frames. I don't remember the exact number. It was maybe up to 4 without really any significant loss at all.
Any more questions? Let's thanks the speaker again.